Okay, welcome back. So the next part of the chapter after predicting products are mass-to-mass relationships, which we call stoichiometry. So it says, if we know the moles of reactants, then the balanced equation will tell us the moles of the products, so we can predict how much mass of product we're going to get. All right. Well, I'm going to start off by telling you there's actually two different types of reactions in chemistry. Those that follow stoichiometry. And stoichiometry means we're going to use a single arrow when we write our equation. So A plus B produces C. We have a single arrow, and what the single arrow means is 100% yield, or approaches 100% yield, which means all of our products become reactants. Most reactions, however, follow what's called equilibria principles. And in equilibria, we are limited by our environment. For instance, our environment can only hold a certain amount of carbon dioxide before other things have to shift. And in those reactions, we would write A plus B, and then we use these reversible arrows to get C. And we're going to study this in the fourth marking period. And what the double arrows mean is that we get much less than 100% yield. So, stoichiometry, reactions that follow stoichiometry, combustion reacts very nicely and goes to 100% yield. Things that produce a precipitate. Generally, and I'm going to put a star next to here, a lot of reactions that produce water molecules on our planet have a strong driving force. So therefore, things like strong acid reacting with strong base, and we'll talk about that in neutralization in this last video for this chapter. Those things have a strong driving force and produce 100% yield. And then most of your redox reactions, and I say most, it has to produce a voltage of over 0.1 volts. So a lot of our reactions do follow stoichiometry, but far more follow equilibria. And you studied equilibria a little bit in biology. They probably mentioned something called homeostasis, which is an equilibrium principle. All right, so how does stoichiometry work? Glad you asked. Suppose we had the following reaction. We're going to take hydrogen gas and we're going to react it with nitrogen to produce ammonia. So I'm going to balance that equation. Now, whenever we deal with the reactants, there are going to be two types. One that we call the limiting reagent. And the limiting reagent is the one that runs out first. It's almost impossible for us to mass and be able to, in the lab, create the correct ratios. We're always going to be off by a little bit. So one of these chemicals is going to run out first, and we call that the limiting reagent. The one that doesn't run out is we call the excess reagent. So we're going to start with problems that only involve an excess reagent. For instance, they may say something like, oh, all right, let's run this reaction where we have 5.2 moles of hydrogen, and we're going to react it with nitrogen. They want you to predict how many moles of ammonia will be produced. Okay, well, we know that hydrogen is the limiting reagent here. How do I know it's the limiting reagent? Because it's the only one that's mentioned. And when they mention the other chemical without giving you an amount, that means automatically this is the excess reagent. So it's the limiting reagent that determines how much product you get. So I'm going to use the technique that we learned. I'm going to start with what they give us, 5.2 moles of hydrogen. And I'm going to set up a conversion factor, moles of hydrogen. Now, if I want to find out moles of ammonia, will the balanced equation tell me that? And the answer is yeah, of course it will. Let's take a look. We have 3 moles of hydrogen, we have 1 mole of nitrogen, and we have 2 moles of ammonia. So we can set up that fraction. 3 moles of hydrogen, as long as we have plenty of nitrogen in excess, will produce 2 moles of ammonia. So get out our handy dandy calculator, 5.2 times 2 divided by 3. I get 3.5 moles of ammonia. That's our product. So they could ask you mole to mole ratios because the balanced equation, that is our mole ratio. For every 3 moles of hydrogen, we need 1 mole of nitrogen, and that's going to produce 2 moles of ammonia. Mole ratio is the balanced equation. So if we want to go from one chemical to another, we need that balanced equation to tell us what the mole ratios are. All right, so suppose we do the same reaction, and they say, all right, we're going to do 106 grams of nitrogen, and we're going to react that with excess hydrogen. I want to know how many grams of ammonia are produced. Okay, well, again, we need to know the limiting reagent, and if they only mention the amount of one chemical, one reactant, that's automatically our limiting reagent. Of course, in this problem, they told you the hydrogen was in excess. So we're not worried about the hydrogen. It means we have more than enough hydrogen to run the reaction. So our limiting reagent is going to limit how much product we get. So I'm going to start with what they give us. Now, in order to be able to use a balanced equation, just like formulas are mole ratios, balanced equations are also mole ratios. So I'm going to convert that to moles of nitrogen. Now I can use my balanced equation, right? If I know how many moles of nitrogen we have, I can predict how many moles of ammonia we get. And then I can come back and I can convert those moles of ammonia to grams of ammonia. All right, so now I just got to go back and fill in the numbers. All right, so 1 mole nitrogen, I looked that up on the periodic table. That's 28.014 grams. And according to the balanced equation, for every 1 mole of nitrogen we consume, we produce 2 moles of ammonia. And for every 1 mole of ammonia, we get 17.014. I'm going to check that though. So let me do nitrogen is 14.007 plus 3 times 1.008 for hydrogen, 17.03, not 04, 17.031. All right, so that's going to give me 106 divided by 28.014 times 2 times 17.031. And so 3 sig figs, my answer is 129 grams of ammonia. Okay. All right, so what else could they ask you? Well, they could ask you about energy. Energy is associated with the reaction also. Let's say, for instance, they talk about 2 types of reactions. We have an exothermic reaction. Exothermic means it releases heat. So if it releases heat, that means heat is a product. So we could put heat on the product side of the equation. We could do A plus B produces C. And let's say we do 42 kilojoules of heat energy. Or if it's exothermic, that means delta H is going to have some sort of negative value, some sort of negative number. So for instance, we could also say that the delta H for this reaction is negative 42 kilojoules per mole reaction. What mole reaction means, let's say for instance, this A had 2 moles in it. Then it would be negative 42 kilojoules per 2 moles of A. If there were 3 moles in the balanced equation associated with B, then we would say negative 42 kilojoules per 3 moles of B. Or if it was 1 mole, we would say negative 42 kilojoules per 1 mole of B. It goes by the number of moles that are in your balanced equation. If it's endothermic, that means it absorbs heat. So heat is a reactant. Or they could give us a delta H value, but the delta H value would have to be some sort of positive number. So here's an example. Suppose we had 3 moles of A plus a mole of B. produces a mole of A3B. If it's endothermic, we're going to put the heat on the reactant side. So let's say that this is 120 kilojoules, or we could say delta H is equal to positive 120 kilojoules per mole reaction. So that means, for instance, that we would have 120 kilojoules per every 3 moles of A that are consumed. So let's go back to our little reaction with hydrogen and nitrogen. And let's say that this is endothermic, right? And I'm just going to make up a number here. Let's say 64 kilojoules per mole reaction. And they say, all right, we are going to react 134 grams of hydrogen. I want to know how many kilojoules of energy will be absorbed. All right, well, first of all, we know that the hydrogen must be the limiting reagent here because it's the only chemical they mention, and that the nitrogen must be in excess, and that we have enough heat to run the reaction. So I'm going to start with what they give us. 134 grams of hydrogen. And we're going to convert that to moles so that we can use our balanced equation. And according to the balanced equation, for every 3 moles of hydrogen, we have to absorb 64 kilojoules of energy. So now just go back and look up the mass of hydrogen. 1 mole of hydrogen is 2.016 grams. So I can do 134 divided by 2.016 times 64 divided by 3. And I get 1,417.98. So I'm going to do 3 sig fig. So 1,420 kilojoules of energy. And that's really all there is to it. Now, they could ask you questions like, hey, how much heat is absorbed when we produce 5 moles of ammonia? Or how much nitrogen will we need to produce 150 grams of ammonia? I mean, there's a lot of different starting points and ending points. But ultimately, it's just a matter of going through the problems and practicing. They're all the same technique. And again, this is just when you have one chemical listed for the amount, consider that the limiting reagent. And in other videos, I'll tell you how to deal with percent yield and when they mention multiple